Hello everyone. Today we're going to implement Fibonacci series in VHDL using finite state machine. So as you can see, there's an empty folder. By the way, I'm using VHDL for simulation. I've made a simple make file so that I will be able to generate the VHDL file. So these are just simple VHDL commands that I have made inside a makefile. So I've made an empty folder. Inside this empty folder, I'm going to create this Fibonacci main source code. I'll be using this one for plus 5v2.phd, and together with this one, another file for this test file, Fibonacci 2 underscore test bench.phd. So in the main implementation for the Fibonacci series, I will be making the input and output inside an integer. So for that, we're going to be using the library IEEE, use IEEE std logic. Use IEEE numeric std. So entity SIB2 and SIB2. So port, first we're going to define clock, reset, and start. These are going to be inputs as std logic, just 1 bit is num. Oh, this is also input. This snum parameter is defining how many values of Fibonacci series we want to calculate. So I'm taking this one as an input, and maybe we can select this one as an integer. And y out, this is output. This is also I'm taking as an integer, and also I am making a signal code then. So that the calculation is finished, this will be 1. Logic. Okay. So now the input and outputs are defined. So we're going to make architecture behavior FFID 2 is begin and end behavior. These are the simplest structure of architecture inside the VHDL file. So I'm going to define the state type. So I'll be using 3 steps. First one, idle. The second one is start for initializing the first 2 values of Fibonacci series. The third one would be is run and is stop. So I will be calculating the Fibonacci series inside is run state, and when the calculation is finished, then we're going to come to the stop, and then the calculation is finished. So in this method, I'm using the 2 process method. That's why we are going to use the current state and the next state. So I'm defining 2 signals. First one is state for current state, and the next state. This will be step 1. Maybe I can initialize this state as idle. The next step, I will just define it. And now we are going to define the registers that we're going to store the values, and we need to pass them between the states. So because the Fibonacci series is using the two previous value, that's why we need two register values. So signal y out register and y out register 2. These are registers, but we need to define the y out signal also. So y out 1 and y out 2. We can define these signals as integer, but in order to make sure that data type, we can define a subtype and make a desired data type. For example, in C, that that there are some int 16 with 16 bits of data type. So in VHDL, we are also able to define such data type. So subtype, I'm defining one data type for that one. Subtype, I'm naming that one int 16 underscore t as integer range. So the range is -0 to 768 to 767. That's because I'm using, so 16-bit is from -2 to the power of n minus 1, so 16 minus 1 is 15, until 2 to the power of 15. 2 to the power of 15. So 2 to the power of 15 to the power of 15, it's 32,768. So that will be from -32,768 to 32,767. That's what we have defined here. So the registers, I'm also defining them as int 16t, and I'm initializing it equal to 0. And we also need to define a counter, signal count register. We can define both of them also as int 16 underscore t and initialize into 0. So these were the initialization of the data types and input output. Now coming to the implementation of the finite state machine itself. So we are using two process method. So the first method is sequential process, which sequential process, which is a sequential process. So sequential process, which is dependent on clock and reset. Begin and process, sequential process. So I'm making this one as synchronous, so that's why I'm including the rising age, the beginning, like this. If clock event and clock is equal to 1, then we can also write this one like this, utilizing age of clock. So, and if writing age of clock, now if reset is equal to 1, then state is going to be idle, and also we have to set the registers equal to 0. So state is equal to idle, while out register, while out register is equal to 0, and while out register 2 is equal to 0, and also counter count register is equal to 0. Process, okay, that has to be into okay. So in case reset is equal to 1, then state is going to be in idle position, and all the registers are equal to 0. So in else condition, state is going to go to the next state, and y out reg will be equal to y1, y out 1, y out reg 2 is equal to y out 2, and counter register will be equal to count. So we have initialized the register, and in case of clock edge, so in case if there is a clock detection, then registers will be updated and the state will be also updated. So now we need to implement the combinational process, which is required for finding the next state, for finding or calculating the next state. So combination process. So the sensitivity list for this one is state is none, stored y average, y average 2, count range, combination process. So now after defining the combinational process, we need to initialize the default values for each state and for next state and other variables. So next state is equal to idle, y out 1 is equal to 0, and also y out 2 is equal to 0. I'm also making the down signal equal to 0. So these are the default values. Now we can start to define what happens in each state. So case state is when. So copying these. Start some. And we can add now we can define what happening in each state. So when idle, we can say that y out 1 is equal to 0, y out 2 is equal to 0. But then whenever the state reaches the idle position, it means that either the calculation is not started or it is finished. So we can define the done signal inside idle state as 1. And now we have also the start signal. So here, as a sensitivity list, we can use it here. If start is equal to 1, exit state is going to be start. So in is start, we can initialize the first two values of the Fibonacci series, which is equal to 0 and 1. So y out 1 is equal to 0 and y out 2 is equal to 1. And I'm also initializing the count to be as is now, because we need to calculate the number of Fibonacci series based on the input from the user. After initializing this value, I will say that the next state will be S1. So S start is also finished. And now in S run, I'm saying that if count is greater than 0, then y out 2 will be equal to y out register, which is the previous values of y1 plus y out register 2, y out reg 2, which is the previous values of y out y2. So this is the main function of Fibonacci series. So then the next values is the sum of the two previous values. Now we have to update y1. Y out 1 is equal to y out reg 2. And also we have to reduce the count by 1. So I'm saying count is equal to count reg minus 1. So each time I'm reducing the count, and when it is equal to 0, I will go to a stop. So saying if count is equal to 0, then next state is equal to is the stop. So here in this stop, I don't have anything to add, but if there is any other calculation, you can add it here also. For example, the last bit, sometimes you're calculating the thing, but the last bit, you need to do some other calculation also in this stop button. So now, since we don't have any other calculation to make, I'm just going to the next state. So the next state is equal to height and end case and end combinational process. There's a syntax error. So after making the source code, we also have to make a testbench file for this one. So for testbench file, I've made this fib2 underscore testbench for this one. So we also need to use library IEEE, use IEEE.std and use IEEE std.now. So entity fib2 underscore t2 is and fib2 underscore t. So since it's a testbench file, we don't have any input and output, so that's why we're not adding anything here. Port is 80. So but inside architecture, we need to define the component. Architecture fib2 underscore t is begin and end architecture behavior and of list and behavior. So here we need to add a component fib2 is and component fib2. I'm going to copy the port definition, add it here. So now we need to define the corresponding signal. I will define the signal clock, reset, and star, and done. These are all std logic, and I can initialize it to 0. Is num. You can also define it as a signal. Signal is num. Then make it as integer and equal to 0. You can also make a subtype of int16t, but for the sake of simplicity, I'm using here integer. And signal by out. This one also I'm looking at as an integer, which is 0. And also for the generation of clock, I'm using a constant clock period. It's time, and it's 10 nanoseconds. A clock period of 10 nanoseconds means that I'm making a clock frequency of 100 megahertz. So you can use different clock signals or clock frequency depending on the timing period. So first we need to generate the clock. So I'm saying that since we have defined this signal clock, it is initially 0. So I'm saying clock is not of clock after clock period divided by 2. So this single line is going to generate a clock with a frequency of 100 megahertz. We also need to initialize the unit under test. So T is equal to instantization. So we don't need here entity words of FIB2 from this one. So port clock is mapped to clock, reset is equal to reset, start is equal to start, is none y to y, and then to y. Be sure to define all these signals on the right side here. As you can see, I've defined all of them here. So, and now you have to make the simulation of these things. Process. This is also a process. We don't need any sensitivity list. So wait means after the simulation is finished, we're just stopping the simulation. This wait at last part of this process means we're stopping the simulation after the code has reached here. So I'm leaving is none as, for example, I want to see 10 Fibonacci series. Initially, I'm checking the reset and start signal. So first, I'm making reset equal to 1. When reset is equal to 1, I shouldn't get any Fibonacci series. The output should be 0. And start is equal to 0. So I'm waiting for clock's period, maybe clock period, and then I'm making reset equal to 0 and start equal to 1, and wait for clock period of maybe 25 clocks. So initially I shouldn't see any result. After 5 clocks, then I should see that the Fibonacci series is starting to show up, and up to 10 values I should get. So we can use it like this. Since I'm using VHDL, I can use this make file, but first of all, I'm just going to demonstrate how we can use the VHDL. So I'm in FIB2. I'm going to insert this folder here. So I'm writing VHDL minus A, FIB2.vht, and FIB2 underscore td.vht. So this file is going to analyze the two file. There is a spelling mistake. I should have written that VHDL. Okay, it is analyzed now, and also now we should elaborate it. So VHDL minus E FIB2 underscore TB. Be sure that we're just elaborating the simulation file. Okay, now it is elaborated. Now we're simulating VHDL with minus R FIB2 underscore TB. Then we need to write the stop time is equal to, for example, I'm saying 500 nanosecond, and wave is equal to wave 1.2HW. So it's going to produce a simulation for 500 nanosecond, and I'm generating a waveform file so that we can see the output. So it's done. Now we're using GTK wave. Now, as you can see, the file is run, and we can see the test bench file, and here it is also unit on test. We can see that the simulation is per 500 nanosecond. I can bring here the clock signal. This is up to 500 nanosecond. Reset. Start. Snum. Y out. Done. State. Next state. Y rate. Out rate. Y out. Count. Countage. So, as you can see, there is a little not okay. Maybe I should see where is the problem. And okay, so I have found that there is a little bug. This inside the combinational process, next state has to be assigned to state, not idle, because every time you're coming, initially it has to update the next state to state, and also at the end you have to assign the y out to the y out too. So now, as I have said previously, you can run the files like this: VHDL minus a, and the name of the two file. Oh, sorry. So inside I'm having the two files, so VHDL minus a and the name of the two file. This has to be VHDL. So now it is analyzed, and VHDL minus e lv2 _ test bench, and VHDL minus r lv2 _ tb with a stop time of 500 nanosecond, and we one step. So sorry, there has to be to here. Now it is simulated. So as you can see here, it is wave 1.ghw. We can show it using GTK wave. GTK wave 1.ghw. So as you can see here, simulated. You can see here the clock, 500 nanosecond. Set, start. So as you can see, there is a clock signal, reset signal, and start signal. So it's num. It shows how many series of the Fibonacci series has to be calculated. And now you can see the state. So it is in idle position. When it start is equal to 1, it goes into its start, and then it's run. When calculation is complete, then it's a stop, and then in idle position. We can see that then signal also in idle position, then is equal to 1. So we can change the duration to 200 nanosecond to see it better. Yeah, it's a start, it's run, it's a stop. Also the output, I can see it here. So 0 in idle position, when start is equal to 1. The state machine starts to calculate 0, 1, 0 plus 1, 2, 1 plus 2, 3, 2 plus 3, 5, 3 plus 5, 8, 8 plus 13, 21. So in that one, you can also show the count here: 10, 9, 8, 7, 6, 5, 4, 3, 1, 0, 1, and 0. And you can see that it's calculating here, right? So the make file that I have made, I can save this setting as wave setting inside the FIB2 inside the folder. Yeah, and when I run the command make run, then I will get the same. For example, here I'm coming inside the test bench and I say that I want to see, instead of 10 value, I want to see 15 value. So directory, coming one step back, and here FIB2. So make run dir equals to name of the file, name of the folder, and then name of the file. Because name of the file and name of the folder, both of them are the same, just by running this command, you can get your simulation in one. So now it's in 500 nanosecond, so 200 nanosecond, it's almost finished. 250 around 215. So is known is equal to 15, and y done is here equal to 1. So from here until here the calculation was done. Count is equal to 11. So from 15 till 0, y out 0 1, and it's calculating the Fibonacci. And thank you very much.